We've been using a couple integral formulas to evaluate our definite integrals, at least once we decided we didn't want to use the limit definition of the integral anymore. One of them was the integral from a to b of x dx. And although we didn't calculate this using the limit definition, and we won't, we did calculate the integral from 0 to b of mx dx, which is almost the same thing. So even though we haven't calculated this, we've done something very similar, so I won't calculate this. But another one that we've been using is this one, so the integral from a to b of x squared dx. And this one we used actually several times, so it would be worth it to see why this comes out to be what I said it should be. And the only tool that we have to use to calculate this integral is the limit definition. I mean, if you look at the region that we're talking about here, right, x squared is a parabola. And so what we're asking for is the area from a to b under this parabola. And like, I don't know off the top of my head a nice handy formula for the area of this. Well, I do, but probably you don't. So using the limit definition of the integral is the best we can do. So let's see what we get. This is going to get pretty ugly, but we have the tools to do it. So let's do it. Limit as n goes to infinity of the sum from I equals 1 to n of, right, so we have to write the squared function, and we have to put x sub I in here. So that's a plus I times delta x, which is b minus a over n, and then times delta x on the outside, and that's b minus a over n. All right, so let's see what we get. Limit as n goes to infinity of the sum. You know what? Why don't, right off the bat, this b minus a over n doesn't depend on I, so let's factor it outside of the sum. So that gives us a b minus a over n out here. Now inside of the sum, from I equals 1 to n, let's multiply out this squaring. I don't really see any way around that. So we're going to get first squared times twice the product times second squared. So a squared plus 2 times a times I times b minus a over n, okay, plus the second part squared, so I squared times b minus a over n squared. Okay, so it's going to get worse before it gets better, but let's see what to do next. The only thing that I really see to do next is split this sum up and sort of distribute the sigma. So that's going to give us limit as n goes to infinity of b minus a over n times the sum from I equals 1 to n of a squared plus the sum from I equals 1 to n of 2ai times b minus a over n plus the sum from I equals 1 to n of I squared times b minus a over n squared. Okay. Next, now that we have all these sums written separately, let's factor out any common factors for each one of them. So limit as n goes to infinity of b minus a over n. For this first one, we can factor out this a squared. So a squared times the sum from I equals 1 to n of just 1, right? We factored out everything, so that leaves a 1 behind, plus in the second one, we can factor out everything except this I right here. The I has to stay inside the sum because that's what changes for each term in the sum, I. But everything else we can factor out. So 2 times a times b minus a over n times the sum from I equals 1 to n of I. Plus, and then for the last one, this b minus a over n all squared, that is what we can factor out. So b minus a over n squared times the sum from I equals 1 to n of I squared. Okay, what next? Well, if you look at each of these individual sums, here, here, and here, we have nice formulas for those. So let's use those formulas. So limit as n goes to infinity of b minus a over n times a squared times, so for this first sum, adding 1 to itself n times, that gives us n, plus 2a times b minus a over n. Now the second sum from 1 to n of I, that's n times n plus 1 over 2. And then for the last one, b minus a over n squared. And then the sum from 1 to n of I squared, that was n times n plus 1 times 2n plus 1, all over 6. All right. For each term, let's see. Maybe what we should do now is distribute this b minus a over n, like that, just to get all of the n's together in each term. So limit as n goes to infinity. Actually, why don't we only distribute the denominator? Let's keep the b minus a all the way over here, but distribute that 1 over n. So a squared times n over n is a squared. In the second term, we get another factor of n in the denominator. So there's the 2a. There's this b minus a in the numerator. There's a 2 over here in the denominator. While we're at it, why don't we cancel those? Then in the numerator, there's an n times n plus 1. And then in the denominator, there's this factor of n plus or times the factor of n in the denominator that we're distributing. So that gives us an n squared in the denominator. Okay, for this last part, in the numerator, we have a b minus a squared, and also the 6 over here. In the denominator, there's 2 factors of n right here. Remember, this n down here gets squared. And then also the factor of n in the denominator that we're distributing, so that's an n cubed. And then in the numerator, there's n times n plus 1 times 2n plus 1. All right. So now let's calculate the limit. If you look at the parts of this that have n in them, right, these are both rational expressions in n. And there's a nice trick for evaluating the limit of a rational expression at infinity. And that trick is, you probably saw this in Calc 1, look at the leading term in the numerator and denominator. So in the numerator, if we did multiply this out, we'd get n squared for our leading term. And in the denominator, the leading term is n squared. And that's 1. And this is the limit as n goes to infinity. All right, now let's do the same thing for this last piece. In the denominator, the leading term is n cubed. In the numerator, if you imagine multiplying this all out, your n cubed term would actually have a 2 in front of it because of that 2 right there. And so the limit at infinity is 2. All right, so now we can write down the limit. It's b minus a times a squared plus, let's see, we have a times b minus a times the value of this limit, which is just 1, plus b minus a squared over 6 times the value of this limit, which is 2. And while we're at it, why don't we simplify this? We get a 3 in that denominator there. Okay. So at this point, this looks like a bit of a mess, but why don't we, first of all, let's factor out a 1/3 from this stuff in brackets just to get this denominator out of the way. That gives us 1/3 b minus a. And now I have to factor out a 1/3 from the brackets, so that gives me 3a squared plus 3a times b minus a plus b minus a squared. Okay? And now it looks to me like maybe what we should do is multiply everything out in the brackets and simplify it. So 3a squared plus 3ab minus 3a squared. That's nice. This stuff cancels. Plus, and then multiplying out this piece, we get b squared minus 2ab plus a squared. Okay, so 1/3 times b minus a. All right, so let's see, we have b squared, and combining the ab terms, we have plus ab, and then plus a squared. Okay, I guess there's no getting away from multiplying out all of these a's and b's. So when we do that, so distribute b through everything, we get b cubed plus ab squared plus a squared b. So that's distributing this b. Now let's distribute the minus a. Minus ab squared minus a squared b minus a cubed. And a lot of this stuff cancels. These cancel, and these cancel. And finally, we're left with 1/3 times b cubed minus a cubed. And that's what I said we should get. Remember, we were calculating the integral from a to b of x squared dx. And this is the formula that I used in an earlier video, and now you can see that this formula is correct.